welcome back. Today we're going to talk about model building and hyperparameter tuning. In the previous session we spent some time trying to build a classification model. In particular, we built a logistic regression model, but we didn't spend time fine-tuning that model. We just used the basic model. So today we're going to learn about techniques for hyperparameter tuning or fine-tuning of these models. So I've written some code for you that I'm going to walk through. As usual, the first thing we're going to have to do is to import the modules that we're going to need to use. And just like anything else that we've done, scikit-learn has modules for most of the common tasks in machine learning. So today's focus is hyperparameter tuning, and one common technique for hyperparameter tuning is grid searching. There is other techniques such as random searching. Grid searching is kind of a simpler method and commonly used. So for today we're going to focus on grid searching. So from scikit-learn model selection, I'm going to import my GridSearchCV. And again, this is part of the model selection module because the purpose of fine-tuning is to select the best model can. So I want to keep the model the same, but try the same model with a variety of different parameters, different configurations, and see which one is performing the best. So it's a search process. I'm searching for the best possible model. So if I'm trying to build a logistic regression model, what would be the best configuration for that logistic regression model? And I'm also importing the pickle module because at the end, when I'm happy with my model building process and I have a model, my finalized model, I'm gonna need to save that model, and that's the final output from my work, and that's a trained model, and someone could load that model and start making predictions with that model. So if you remember from last sessions, without doing any hyperparameter tuning, when we built our basic model, when we did a tenfold cross-validation, the accuracy that we had from that model was around 94% plus minus some deviation from that. And our model is already performing at an acceptable level, but we want to see if we can push the limits of that model a little bit higher and kind of see if we can improve the performance a little bit. The first question you might ask is, what are the parameters that I can fine-tune? And for that, I'm trying to fine-tune my classification pipeline, and my classification model is just one part of it, which is what I'm focusing on today, but you could fine-tune any part of your pipeline. And if you remember, in my pipeline I have a standard scalar process. I'm applying PCA, and at the end, once I'm done with pre-processing my data and reducing the dimensionality of my data, I'm using a classifier, a logistic regression model. So I'm going to focus on fine-tuning a couple of hyperparameters from my logistic regression model, but you could fine-tune any of those modules. And just to see what are the options for fine-tuning, you can just call this get params or parameters model, and it's going to tell you, it's going to return back a dictionary. And so if you print the keys of that dictionary, this is going to be a list of everything that you can fine-tune. And scikit-learn is using this convention where you have the component name, 2 underscores, and then the name of the parameters. So I called my logistic regression model classifier. So as you are looking at these values, you see classifier underscore underscore penalty, or any of these other parameters. So these are basically, the first piece is the component you are trying to fine-tune in your pipeline, and the second piece is the actual parameter name. So, but basically these hyperparameters are knobs. Think about it as knobs that you can basically change the way you would fine-tune any device. And you can increase or decrease the values of the hyperparameters, and it would impact the performance of your model. And like I mentioned, it's a search process, so you change these knobs and you come up with different configuration, different set of values, and it's an empirical process. You run an experiment, you'll need to run many experiments, but each experiment is basically using one set of values, building a model, and everything else is the same. It's going to use cross-validation to measure the performance of the model, the model with the new configuration, and that's one model. And then you keep doing this, and at the end you're going to look at all your results and you're going to pick the one that's your best performing model. So for now, let's focus on a couple of these parameters. I'm going to try to fine-tune the classifier penalty, which is this one here. This is one of the parameters that I can fine-tune. And also something called the C parameter. This is my inverse regularization strength. So you don't need to fine-tune every single parameter here. Usually there is a few parameters that have the most impact on your model, and you would learn about these by experience, so you'll know which parameters have more impact on the performance of your model. For logistic regression model, it's very common to focus on the type of penalty, the form of penalty, and so this is a penalty is a term that gets added to your objective function. That's what behind the scene is optimized to give you your best performing model. And so we're sometimes when models overfit, that's because your models are complex. And so regularization is a method to basically help reduce complexity of your model. So basically you're not allowing your model to get too complex. And so for a logistic regression model, if you think about a logistic regression model, when you build that model, really what you are looking for is the weights for that logistic regression equation. And when those weights get bigger, what that means is that they're having more impact on the final output of your model, the final score that your model is going to generate. And you don't want to allow your models to do that, to get too complex. And so basically what you're saying is, I'm interested in a model, in a more balanced model, a model that basically doesn't get too complicated, doesn't use weights that are very large. And so the way to do that is to add a regularization term to your objective function, and instead of just optimizing your objective function, and again, you don't see any of this because all of this is hidden in the code that does this for you. And if you're using scikit-learn, all these mathematical details are hidden behind the APIs that you're using, but it's very useful to have an understanding of the theoretical concepts behind the scenes. So but essentially that's what's happening. Instead of just optimizing your objective function or loss function, you are trying to now optimize a new function, which is your loss function or objective function, plus this new term, new mathematical term that you add to that equation. And L1 and L2 is really referring to the form of the term that gets added to your loss function. Sometimes these are called L1 norm or L2 norm. But really in L1, you are just adding the weights, some of the weights to your model, your loss function, and basically when your weights get larger, it will overall increase the value of the loss function. And so in an effort to decrease the loss of the model, your model is going to try to make the weights smaller. But then you could also do the L2 norm regularization, which instead of just using the sum of weights, is going to use the squared values of the weights. And as your weights become larger, the penalty is going to become even much larger. And so that's kind of the way of saying the penalty is not linear. It's actually growing much faster than the rate at which you are growing these rate values. So L1 and L2 refer to the form of the regularization that you're adding to your model. So you can also define the strength of the regularization in addition to the form of the regularization. And scikit-learn is using this parameter C, which is the inverse of regularization. So it's 1 over the regularization strength. And so it's very common to use numbers in this scale. You are starting from something like 10 to the minus 4, and then 10 to the minus 3, and 10 to the minus 2, etc. And so when your numbers are small, 1 over a small number is going to be a large number. And so the smaller your number, the larger the strength of the regularization. You're heavily regularizing your model. And at the end of this range of numbers, you have a large number, and so 1 over a large number is a small number. And basically what you're saying is, I just want to regularize my model just a little bit. So this is the strength. Okay, so that was a little bit of theory behind the scene, but from a programmatic point of view, we have this, we are forming a grid, and a grid is a combination of all possible values. You have different parameters, hyperparameters. Every hyperparameter has a number of possible values that it can take, and you decide what those values are. And so, for example, for classifier penalty, our options are L1 and L2. For the inverse of regularization strength, we have a list of values, and so here I'm using 8 different values, and we are trying to form a grid. A grid is basically all possible combinations of these things. So I have 2 parameters. One parameter is taking 2 values. The other parameter is taking 8 different values. So if you multiply these 2 values together, you have a combination of 16 different values, or 16 different configurations that you can try. So basically you are going to say, here is the first configuration, build a model with it, test the model, log the performance of the model, and then move on to the second configuration. And at the end of the process, you are going to have a range of models, and you can pick the one that's the best performing model. We are using this GridSearchCV function, and it's called GridSearchCV, CV standing for cross-validation. You're already familiar with the concept of cross-validation from the previous videos. And as you can see, I'm fine-tuning my classification pipeline, and here is my grid. As you can see, my grid is a list of things that I want to fine-tune, hyperparameters that I want to fine-tune, and every element of the list is you see this dictionary in the list, and basically what I have as the key is the name of the parameter that I want to fine-tune, and then possible values. And then I have my second hyperparameter, and then the range of values. So these 2 lines of code together define my grid, the 16 combinations that we talked about in this particular example, and then I'm passing that to GridSearchCV, and basically what I'm saying is, for every one of these 16 configurations, build models and track the performance of that model, and then at the end tell me which one is the best model. And the cross-validation is 10. This refers to the 10 folds. You're already familiar with this concept of cross-validation. So what's going to happen is that GridSearchCV is going to build 10 models per configuration. So in our example, we have 16 different configurations, and so for each one of these configurations, GridSearchCV is going to do cross-validation, which means instead of just building one model per configuration and reporting that back as the performance of that model, it's going to build 10 different models, 10 folds. So if you remember, one of those 10 folds is going to be called the test fold or validation fold. The other 9 are going to be used as training, and so you're going to rotate the test fold or validation fold, and at the end you're going to have 10 numbers, and you're going to average your performance over those 10 numbers, and that's what you use to report as the performance of that model. And we talked about this being a more stable, more reliable estimate of how well your model is performing. And so grid search with cross validation is going to take a lot of computational resources and time, because if you think about it, and this is a small example, but if you think about a real large scale experimentation, this could literally take days, or if not weeks, for very large models to do this, because even in our small example, we are only fine-tuning 2 parameters. We could fine-tune many parameters, and beyond that we're just using a few values. You could extend this and even add more values to the grid, and then your number of configurations, number of possible configurations, here is 16, it's small, but your number of configurations get multiplied by your CV parameter, which here is 10. So even in this small example, I'm building 16 times 10, 160 models to decide which configuration is the best. So it's a lot of models that you build to select the one that's your best model. But you can see how clean and nice my code is. In just a few lines, all this theory that I talked about, all these different things are happening within a few lines of code. So once you define your grid, once you have your GridSearchCV object, you can just feed it to your train data, just like any other model. You are passing your the x and y for the training data set, the vectors, plus the ground truth labels. When you run the fit, all those experimentations are going to happen, and then you can basically print some reports. You can get the best score, and you can get the best parameter value. So basically you can see which particular set of hyperparameter values resulted in the best model. So in this case, the best performance that we got was 0.95, which is a little bit higher than kind of what, still similar, but maybe a little bit higher than what we had before at 94%. And then the hyperparameters that generated our best result is a inverse regularization value of 1 and a penalty of L1. And again, this is a very experimental process. That's what we do, experiments. You can't just analytically think about this and come up with the best possible values. Over time, with experience, you might be able to make good and educated guesses as to, for this kind of data and this kind of model, usually this is the range of values that works best. But at the end of the day, this is a very experimental process, so you have to run the grid searching. All right, so now that I know what the best parameters are, what I'm gonna do, I'm gonna retrain my model again. And you might ask, we already have our best model. Why are we refeeding our model here? And the answer is, if you remember, the process that was used in my GridSearchCV is CV, cross-validation, which means I divided the data into 10 folds. The system used 9 of those for training, and the testing result was obtained from the remaining fold. And so even your best model was only trained on 9 out of 10 folds. In general, the thinking is that the more data you have, the better. So now that I know what the values of the best parameters are, like that whole experimentation that I did was because I wanted to get to these 2 values, the best parameter value. Now that I know this, I can build a model using these values that I know are the best values, but now I can train the model on all my data, all tenfold. So I have a little bit of more data to add to my training data. Instead of just training on 9, I can train on all of my training data, all of the tenfolds. And so I retrain the model, and I reevaluate the model, and the evaluation is on the test data. So this is our whole dot data. And as you can see, my accuracy is a little bit higher. From 0.9518, I'm 0.9561, a little bit higher. So my model is already a good model. I mean, at this point, the law of diminishing returns, your model is already performing really well. So you have to put a lot of effort to just increase the performance by just a little bit more, just a fraction of a percentage. So, but as you can see, my model, even on test data, is performing really well. And so this is a good sign. My model is actually generalizing. And so this test data that I'm using is new data that my model has never seen before. It was not part of my cross-validation, or it was not part of my training. So it's performing well on new data. Now, in addition to accuracy, and we've talked about this before, we're not just looking at accuracy, we want to look at all metrics together: precision, recall, F1. And so what we're going to do here is we're going to print all these other metrics, and you're familiar with this code. All I'm doing is once I have my best parameter values, I'm training a model using all the data, and that becomes my best model. Now I'm using my best model to predict on test data. This is a fair test because my test data, x underscore test, is new data. It's the holdout data. I've never used it before in my training or fine-tuning. So now what I have is the result of predictions for my test data, my new data. And so I can use all these methods that you've seen before: precision score, recall score, and F1 score. And all you do, you just pass two values. It's your predictions and then the ground truth values. And so for every single data point, the predicted value is going to be compared to the ground truth value. If it's a match, then that's a good decision. If it's not a match, it's a bad decision. It's a mistake that your model is making, and depending on the type of the mistake, it could be a false positive or a false negative. So we've talked about all of this before in our previous videos. So what we do here is we just print these new values, and to make it easier to do a comparison, I copied the values that we had before from the first model that we built in this notebook, where we didn't do any fine-tuning. We want to see if fine-tuning had any impact in any of these performance metrics. And so previously our precision was 97%, and you can see our precision still remains 97%. If you look at the third and fourth digits after the decimal point, our precision went up by a little bit. Same precision, a little bit higher, not too much of a difference. But recall, if you look at recall, our recall without any kind of fine-tuning was 88%. Now it's 90%. So this is good. 2% increase is good, especially at this level where your model is already performing well, and you do the hyperparameter tuning and you just push the performance a little bit higher. So this is a good thing. And my F1 score from 0.925, 92%, went up to 0.938. So I pushed the F1 score a little bit higher. Okay, so we have a model. We're happy with this model. We've found the best model we can. We've looked at our accuracy, precision, recall, F1. We're happy with the result. We feel this model is a good model for its intended business use case. So the next step is going to be, now that we have this trained model, let's save it. And so I use the pickle module. I just save the model in a file, and we are done. We have a trained model sitting in a file ready to be used. Now this next cell could be a different application that's using your model. So I could open a new notebook and start working with this saved model, or it could be a web application that's using. So this piece of code is the client. This is who is going to use your model. So you are done. You delivered your model. You found the best model. You saved it, and so you're done. You have a good model waiting to be used. Now imagine this next piece is a web application that's trying to use your model to make predictions. So the first thing you're going to have to do is you're going to have to load that model. So you simply give it the name of the path of the file, and you are loading it. And so this becomes your fully trained model ready to make predictions. And I have two pieces of data that I'm going to use to make predictions. Our data is just that vector of numbers. So whatever features you used for training, it's the same set of features that we use for predictions. So same number of columns of data. But imagine this is new data. I have two data points, and if you remember, this was basically predicting 1 or 0, malignant or benign, and I used two records that I had ground truth for, so I know the correct answer for the first one should be M, malignant, and the second one benign. So what I'm gonna do, I am going to do predictions. So this is my loaded model. I'm gonna say loaded model.predict, and then I'm gonna pass the data value to it, the first one and the second one. And it's useful to look at the probabilities, not just the label. It's not just enough to say my model is predicting this to be malignant or benign, or 1 or 0, or positive or negative. I also want to see how confident my model is. What's the probability? Usually the threshold is 50% if the probability of the positive label is greater than 50%, then the label becomes 1. If it's below 50%, the label becomes 0. So I want to see the probability too. So instead of just predict, I'm going to use predict probab, which stands for probability. And I'm going to print this value. So as you can see, for the first one, I was expecting malignant or 1. And as you can see, the answer I get is 1. And you see my answer in opening closing bracket, that's the least symbol. Because you could make batch prediction. You could predict for 100 records or 1,000 records, but here I just made I predicted on one single value, one single row, so that's why my list just has one item in it. But the answer is 1, and if you look at the probability, it's two numbers. It's the probability of 0 and probability of 1. So what my model is telling me is the probability of this new instance that I wanted to predict on be 0 is 1.75 to the 10 to the power minus 8. Which is a very small number, close to 0. And the probability of it being 1 is 9.99 to the power of minus 1. So which basically means 99%. So basically almost 100%. So what my model is telling me is I'm almost 100% sure this is a 1. If you look at the second prediction, the prediction comes out 0. So my model is telling me the second one, the prediction for the second record is 0, which is correct. And now if you look at the probabilities, the probability for 0 is over 99%, almost 100%, and the probability for 1 is close to 0. If you look at these numbers, this is a number to the power of minus 5. So you have a lot of zeros, a few zeros before you get to any real number. So if you just look at the first few digits after the decimal point, basically what this means is that the probability of this instance being a 0 is very high, and the probability of it being a 1 is very low, close to 0. So this is what we had today. You learned how to fine-tune the hyperparameters in your models to get the best possible model. And today we used grid searching. As I mentioned, there is other methods that you can use. You can use random searching or even more advanced methods like Bayesian hyperparameter tuning. But this should give you a foundation for the concept itself. So now you know what hyperparameter tuning is and how to fine-tune your model. This is a very important process. This can be the difference between a model that's not performing well at all and a model that's performing really well. I've heard people say, a decision tree is not going to work here, or a deep learning model, a neural network might do better, or my SVM model is not working, etc. Oftentimes what I see is that it's really not just the type of model, it's how you fine-tune that model. So in many cases I've seen, for example, a neural network model that was performing at a really low level, unacceptable. When you fine-tune that model, this becomes a really good model, and even it might become your best model. So I've seen models going from not performing at all to performing very, very well when you do this kind of experimentation and you manage to find the right set of hyperparameters. So this is a process that you always have to go through. You build your model with basic parameters. If you get lucky, you're going to get a model that's working. It's acceptable to the business problem you're trying to solve. But if your model is not performing well with the set of parameters that you used, you start to do this kind of hyperparameter tuning and running experiments in search of that one model, that one configuration that's going to give you a model that's performing at a higher level. Thanks for watching this video. I hope you learned something from it.